What if the information we thought was lost forever could actually be recovered? In this fascinating exploration, we dive into the emerging field of quantum archaeology, an interdisciplinary frontier where quantum information theory meets historical research. Unlike traditional archaeology that digs through soil and stone, quantum archaeology sifts through the very fabric of information itself, challenging our fundamental understanding of what can and cannot be recovered from the past. Join us as we uncover how cutting-edge computational methods are revealing ancient voices, lost texts, and hidden knowledge previously thought erased by time. Quantum archaeology exists at the intersection of quantum information theory, computational linguistics, and traditional archaeology. But don't be misled by the name. We're not excavating quantum particles. Instead, this revolutionary field employs quantum-inspired computational methods to recover information that experts once considered permanently lost to time. For centuries, scholars accepted that when artifacts were too damaged, a clay tablet shattered beyond recognition or a papyrus faded to near invisibility, certain information was simply gone forever. Classical information theory, developed by Claude Shannon in the 1940s, established clear limits on data recovery from degraded sources. But quantum archaeology challenges these fundamental assumptions. Drawing from quantum mechanics' no-deletion theorem, this approach suggests that information isn't truly destroyed. It becomes entangled with its environment. What appears as noise or degradation actually contains subtle patterns that, with sufficient computational power, can be disentangled and recovered. The mathematical principles behind quantum archaeology represent a significant departure from traditional restoration techniques. While conventional methods rely on Bayesian probability models, which struggle when signal-to-noise ratios fall below certain thresholds, quantum archaeological approaches employ tensor network algorithms and quantum-inspired neural networks. These sophisticated computational tools can identify correlations invisible to classical statistical methods. The breakthrough moment came in 2018 when MIT researchers demonstrated that seemingly random noise patterns in degraded manuscripts actually contained recoverable information. By training algorithms on vast datasets of historical documents, they created systems capable of distinguishing between genuine randomness and information-bearing patterns masked by centuries of degradation. These systems don't require actual quantum computers to function, though future quantum computing advances will likely enhance capabilities dramatically. Instead, they apply quantum-inspired algorithms on classical computing systems to extract what was previously considered permanently lost information. One of the most remarkable achievements in quantum archaeology involves reconstructing the sounds of extinct languages from archaeological artifacts. In 2021, Cambridge University researchers successfully extracted acoustic information from 6,500-year-old pottery fragments created by the Cucuteni Tripilia culture of Eastern Europe. This technique, called acoustic archaeology, analyzes microscopic patterns in clay that were inadvertently recorded while the potters spoke near the wet clay during creation. These patterns, completely invisible to the naked eye, can be detected using high-resolution imaging and processed through specialized algorithms. As archaeolinguist Dr. Tomas Harkonnen explains, the clay essentially functioned like a primitive phonograph record. We've recovered phonemes from languages that disappeared millennia before any writing system could record them. In one particularly striking case, researchers recovered several words in Proto-Indo-European, the hypothesized ancestor of languages ranging from English to Hindi. What makes this discovery so significant is that these words had previously been reconstructed only through comparative linguistics, and the actual pronunciations differed significantly from scholarly reconstructions, forcing experts to reassess historical language evolution models. The methodology involves scanning pottery surfaces with nanoscale precision using atomic force microscopy, creating detailed three-dimensional maps of surface variations. These maps are then analyzed using spectral decomposition algorithms that separate random variations from those potentially caused by sound waves. The resulting data is processed through machine learning systems trained on how modern materials respond to speech, with adjustments made for the specific acoustic properties of ancient clay compositions. The principles of acoustic archaeology have been extended well beyond pottery to other ancient materials. Stone carvings from ancient Mesopotamia have yielded traces of the ambient sounds present during their creation, including fragments of Sumerian speech and music that haven't been heard for thousands of years. Similarly, researchers have extracted sound impressions from the walls of medieval cathedrals, recovering echoes of liturgical chants that disappeared centuries ago. The stone surfaces, much like the clay pottery, captured microscopic vibration patterns created by sound waves during construction or use. These patterns, preserved in the material structure, can be detected and reconstructed using the same quantum archaeological principles. This approach has opened an entirely new sensory dimension to archaeological research, allowing us to not just see the past, but to hear it as well. The recovered sounds provide unprecedented insights into daily life, religious practices, and the acoustic environments of ancient civilizations, creating a more complete picture of how our ancestors experienced their world. Another groundbreaking application of quantum archaeology involves the recovery of lost texts from palimpsests, manuscripts where original writing was erased and overwritten. While traditional multispectral imaging has been used to reveal such hidden texts for years, quantum archaeological techniques have pushed these boundaries dramatically further. Take the Archimedes palimpsest, a 10th century copy of text by the ancient mathematician that was later overwritten with prayers. When processed with these new quantum-inspired methods, researchers discovered 3 previously unknown geometric propositions that help bridge gaps in understanding how Archimedes approached infinitesimals, concepts that presaged calculus by nearly 2 millennia. The innovation lies in treating ink traces not as binary, present or absent, but as probabilistic distributions across multiple layers of a document. By modeling the chemical degradation processes and how inks interact with parchment over centuries, researchers can computationally rewind these processes, revealing text that has faded beyond the detection threshold of conventional imaging. This approach has revolutionized the study of the Dead Sea Scrolls, where fragments previously considered too damaged for analysis have yielded new texts. At Herculaneum, the carbonized scrolls preserved by the eruption of Mount Vesuvius in 79 CE, long thought to be unreadable, have begun to reveal their contents through similar computational methods. Perhaps the most historically significant application of quantum archaeological techniques occurred in 2023, when researchers applied these methods to documents in the Vatican's secret archives. The team uncovered previously invisible marginalia in medieval manuscripts that revealed unknown intellectual exchanges between Islamic and Christian scholars during the 12th century. These discoveries directly challenge long-standing narratives about the isolation of European thought during this period, suggesting a much more interconnected intellectual world than previously understood. The recovered notes show detailed discussions of mathematical concepts, astronomical observations, and philosophical ideas flowing between Islamic centers of learning and European monasteries. The marginalia, written in tiny script and faded beyond conventional detection methods, includes references to scholars whose works were thought to be unknown in Europe until centuries later. This discovery has forced historians to reconsider the development of Renaissance thought and the cross-cultural influences that shaped Western intellectual history. The quantum archaeological approach revealed these hidden notes by analyzing the chemical composition of the parchment and ink at the molecular level, detecting trace elements and compounds that had reacted with the writing materials centuries ago, leaving patterns invisible to conventional imaging but recoverable through computational analysis. The implications of quantum archaeology extend far beyond traditional historical research. Musicologists have applied similar techniques to degraded wax cylinders and early phonograph recordings, recovering lost performances that transform our understanding of musical history. In 2022, a team at the Eastman School of Music reconstructed previously unplayable recordings of Claude Debussy performing his own compositions. These recovered performances revealed interpretive nuances that changed scholarly understanding of how the composer intended his works to be played. The subtle tempo variations, dynamic choices, and phrasing captured in these restored recordings differ significantly from conventional modern interpretations, offering a direct connection to the composer's original vision. In the visual arts, quantum archaeological methods have recovered underpaintings and preliminary sketches beneath famous works that were invisible to X-ray and infrared analysis. Leonardo da Vinci's preliminary sketches beneath The Virgin of the Rocks revealed alternative compositional approaches that illuminate his creative process. These recovered sketches show Da Vinci experimenting with different arrangements and figures before settling on the final composition, providing unprecedented insight into his artistic decision-making. By analyzing the chemical composition of paint layers at the molecular level and applying quantum-inspired algorithms, researchers can now visualize artistic elements that have been hidden for centuries. Perhaps the most intriguing and controversial frontier of quantum archaeology involves neuroscience. Researchers have begun exploring whether similar principles might eventually allow the recovery of information from preserved brain tissue. While still highly theoretical, Some scientists suggest that memory traces may leave subtle physical patterns that could, in principle, be computationally reconstructed. Dr. Elisa Murnau cautions, "We're not talking about mind reading in any meaningful sense." But the quantum archaeological approach suggests that information considered irretrievably lost might still be accessible with the right techniques. This research direction has attracted significant interest from both medical researchers studying the physical basis of memory and cognitive scientists exploring how information is encoded in neural structures. Early experiments with preserved brain tissue from laboratory animals have demonstrated that specific neural firing patterns can be partially reconstructed from physical traces left in cellular structures. These experiments analyze the distribution of proteins, lipids, and other biomolecules that are modified during neural activity, looking for patterns that correlate with specific memories or learned behaviors. While far from extracting actual thoughts or experiences, these preliminary results suggest that some aspects of neural information processing leave physical traces that persist after death, raising profound questions about the nature of memory and information storage in biological systems. The field of quantum archaeology raises profound ethical questions that society has only begun to address. If we can recover the voices of people who lived thousands of years ago without their consent, what privacy implications might this have? Should there be limits to how we apply these techniques to human remains or sacred artifacts? These questions become increasingly urgent as the technology advances. Cultural heritage organizations have begun developing ethical frameworks for quantum archaeological research. The International Council of Museums released guidelines in 2023 emphasizing the importance of consulting descended communities before applying these techniques to culturally sensitive materials. These guidelines recommend collaborative approaches where indigenous and descended communities participate in decision-making about which artifacts should be analyzed and how the recovered information should be interpreted and shared. The ethical dimensions extend to modern privacy concerns as well. Legal scholars have begun examining how quantum archaeological techniques might impact evidence, law, and privacy regulations. If deleted digital communications can be recovered from storage media through these advanced methods, current data protection frameworks may require fundamental revision. The ability to recover information from seemingly wiped devices or degraded storage media challenges our basic assumptions about data deletion and digital privacy, potentially requiring new legal and regulatory approaches to information security and personal privacy in the digital age. As quantum computing advances, the capabilities of quantum archaeology will likely expand dramatically. Current techniques require enormous computational resources to extract even small amounts of information. Quantum computers, with their ability to process multiple probability states simultaneously, could potentially recover far more lost data from degraded sources. As computational archaeologist Dr. Wei Zhang notes, we're just scratching the surface. The fundamental insight that information thought permanently lost might be recoverable forces us to reconsider what it means for something to be erased from history. In a very real sense, the past may be more accessible than we ever imagined. This reconceptualization extends beyond academic interest into practical applications across numerous fields. Future quantum computers might recover lost medical records to track disease patterns across centuries, reconstruct lost architectural plans of ancient structures to aid preservation efforts, or recover environmental data from ice cores and geological formations at previously impossible resolutions. The development of quantum computing specifically optimized for archaeological applications is already underway, with specialized quantum algorithms designed to process the unique characteristics of degraded historical information. These systems promise to revolutionize not just how we study history, but how we understand the very nature of information itself, challenging the concept that anything is ever truly lost to time. Quantum archaeology represents a paradigm shift in our relationship with the past and with information itself. By challenging the very notion that information can be permanently lost, it opens windows into history that were previously sealed shut. From hearing the actual voices of ancient potters to uncovering lost works of mathematical genius, from revealing hidden artistic processes to potentially glimpsing the physical traces of memories, these techniques transform our understanding of what is recoverable from the ravages of time. As we advance further into this new frontier, the boundaries between present and past begin to blur in ways our ancestors could never have imagined. Yet with these extraordinary capabilities come profound responsibilities. The ethical frameworks we develop today will shape how future generations balance the pursuit of knowledge against privacy and cultural sensitivity. Quantum archaeology doesn't just recover the past. It fundamentally changes our relationship with information, suggesting that in a universe governed by quantum principles, Nothing is ever truly lost. It merely awaits the right methods to be found again. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.